What up, thugs? We are continuing on normal distribution out of 24 AB. And this is just a little recap. I want to do just remind you of what normal distribution is and also do a couple problems with you. One IB style problem, one from the text, and then the time's yours to rock some problems from your home learning. Cool. So what we saw before was that a normal curve describes normally distributed things like people's heights or the length of tails on foxes, right? And most of them will be around the average, and a few of them will be a lot taller, a lot longer, a lot larger. A few will be a lot smaller, and we found that this height right here, the area under that curve, is actually a probability. So you can find these probabilities using a normal curve, and they all behave the same way. If you go from the normal or from the average up one standard deviation, you have a predictable probability of finding that an individual has that height, right? So one standard deviation up, you get 34% of the population will be in there. And also one standard deviation down, the same 34% will be in there, right? And then two standard deviations up, that's another 13% that's in there. And so you could add these two up to find the probability that people are between the mean and two standard deviations up. Right, it would be this and this added together. Fine. Another thing that probably you have surmised by now is that half of the population is above. This is 50%, and this is 50%, right? Now we want to work with not just integer multiples of the standard deviation above and below the mean. We also want to work with little bits of a standard deviation. So I want to know about what about 0.5 of a standard deviation? Well, so that would be here. It's not half of 34. It's going to be more, and so we're going to figure out some tricks on how to do that. Your calculator knows though, right? This is not your job isn't to memorize junk. It's to be able to harness technology to use that to figure those things out. So we can ask nicely about what about half a standard deviation up? What's the probability in there? Cool. So let's try that out with a couple of problems, and hopefully you'll be feeling all right about it. Okay, so here's the first one. This is an old IB question. So a random variable x is distributed normally with a mean of blah and a standard deviation of blah. All right. So maybe to give this some context, mean 450. Maybe let's call that a height of fourth graders in millimeters. 400. All right, so that's their height, right? So that's their average height, which is 450, and the standard deviation just says how spread out it is. If it's 0, everybody's 450, and if the standard deviation is 400, then some are super small and some are really huge. So standard deviation just tells you about the spread. Whenever I see this word, I draw one of these. Bing. Draw a little curve, mark the middle as 450, and then I usually also put, so here's my 450, and I usually also put standard deviation of 20. It's harder to show that, but usually sometimes I'll put a little arrow like that just to put it all in one graphic, one spot. This says find the probability that we pick one of these students and their height is less than 475. Okay, well, 475 is, here's 450, so 475 is going to be greater than that, right? And I want the probability that their height is less than 475, so in here. I guess it's already colored in. Probably don't need to do that anymore. So that sounds like a normal CDF. It's not PDF. If it was PDF, it would be equals, right? I want the probability that their height is exactly 475 right there. No more, no less, but right there, right? And I want this height and this height and this height and this height and this height, add up all these pieces up to 475. So that sounds to me like normal CDF, yeah? So we're gonna throw that one in our calculator. This is sort of the older calculator versions, but oh yeah, nerd life. Go to second distur, right? Because we're talking about a normal distribution. And we're going to go to CDF. The PDF I think about as precisely that value, and CDF is cumulative, so you're adding up all the pieces. So we want CDF, enter. It might have a lower limit here for you. This is a really small number, right? This is tiny. So that's fine. That's 0 essentially. Yeah. And the upper limit is this 475. So let's go down to that 475. The mean is no longer 0, it's 450. And standard deviation, they told us was 20, right? Paste, paste, boom. So 90%, right? 89.4%. Make sure that's 89.4%. Does that look about right? Well, yeah, it's got to be above 50. Here's 50%, so all of this is going to be 50. And you're going to have a more than 50. So as far as we can tell, sounds good, right? 3 significant figures. Okay, so next part is given that the probability is greater than A, that the probability of getting a height bigger than A is 0.27, find A. Okay, well, I'm going to draw this again, right? And so we're looking for some value A, all right, where the probability of getting that a length bigger than A is 0.27. So this side is the 0.27. Yeah. We want to use inverse normal. Inverse normal, like in this one, in this first part, we asked it for 2 bounds. We said this bound, and it filled in for us and gave us the area. So we gave it bounds, and it gave us the area, or the probability, whichever one you want to think about, right? That's normal CDF or normal PDF. This is working backwards. It's giving us the area. So we've got to do the opposite, the inverse. So we've got to talk about the inverse norm, the inverse of normal CDF, right? And it's going to give we're going to put in the area we want, and it gives us the boundary. The problem with that is the calculator is only going to do it in a specific way. If you ask for the probability, it's going to give you the probability, the boundary from 0 up to that boundary. So if you plugged in inverse normal, and if we did this, let's just run it for fun, because it's fun. Area 0.27, the mean is 450, and the standard deviation is 20. If you plug that in like that, it gives you 437, which is below 450. It's here, right? So it would give you 437. What it's done is added up the area from 0 up to this limit, and this is 0.27. And that's not what we want, right? We want the probability that x is bigger than A, so bigger over here, to be 0.27. So what we can do is work it backwards and say, okay, if this is 0.27, then all of this on the upper side of A, then all the stuff on the lower side of A is going to be, well, 100% minus 0.27, right? So 0.73. So we play the same, right? So we're asking it for this area, which leaves 0.27 like we are interested in. So play the same game, dist or inverse normal, but we want 0.73. All the rest is the same. We say go baby go, and it spits out 462, which is above 450, which looks right. So let's check it, check it. Sweet, cool. 6 marks. Neat. Okay. This one's from the text, but it's the same sort of idea. Maybe you want to pause me and try it. Maybe you want to walk through it with me, however you want. But here we go. So rugby players, again, heights of rugby players. It's always something like that. It's like heights of rugby players, or like tail length of field mice, or like ear length of second graders. It's always some, they just plug in different things. Take it with a grain of salt, right? In 1972, arbitrary date to confuse you. Normally distributed, great. Once I see that, I'm not even going to read anymore for the second. I'm just going to do that so my brain starts thinking about normal distribution. Mean 179, so here's 179. Standard deviation of 7, so here's my standard deviation is 7. Okay, find the probability that a randomly selected player in 1972 was at least 175. Okay, here's 179. 175 is going to be on the low side of that, so I'm going to put it there. Yeah, so this is 175. And at least means the 175 is the lower limit for that, so we're interested in the area above it. Yeah, was in at least 175. Cool. So we're looking for this area. Essentially, this is A. This sounds like normal CDF to me. If it was PDF, it would find the probability of getting people exactly 175 centimeters tall. And that's not what I want. I don't want exactly, I want at least, I want bigger than 175. So I'm going to try normal CDF, like that. And now I want my lower limit to be this 175. And I want my upper limit to be as big as possible, right? Now, I know there's some limit to human growth depending on steroidal use, but I think how you put in infinity into this is 1 times 10 to the, that was second EE, and you put 99. It's like the biggest number that the calculator can handle. If you put in 9999999, you'd pretty much get the same thing. Mu, in this case, is 179, and standard deviation is 7, and you go baby go, and it spits out that this area is 0.716. So the probability of your person being at least, so greater than or equal to 175, is 71.6%. Which makes sense because this part is 50%. So this is going to be 50% and some more. Neat. Okay. Great. Let's make sure that's right. 76%. Great. All right. Oh, they even drew a little graph for me. That's nice. Here's B. Different color? Different color. B. Find the probability that they were between 170 and 190. Same idea, right? There. Ew. There's that. This is the same thing, 179. Probably didn't need to draw this twice. 170 is going to be below it, so down here, and 190 is going to be above it there. So this is 170, and this is 190. So we're looking for that area. So that area, we're going to use the same sort of thing. Dister, normal CDF, and we want our lower to be 170, and our upper to be 190, and I think the rest of it was the same. Go baby go. Cool. So 84.3%. We're rounding up to 3 significant figures. It will matter if you're fighting for those like 5, 6, 7s that we want to round to 3 sig figs. So there we go. Cool. Just for fun, I'm going to make up a problem that's the same about inverse normal. So here's my very own C question. It's we want the, let's see, we know the probability of having a person greater than 192? No. Making stuff up. Greater than a certain number, right, is like 25%. Right? What's the probability of that happening? So, where's the cutoff? Okay, so here's the mean. If we try to decode this, this is sort of like saying, I've got some value here, some upper limit. How about n, Gorkevich? How about n? And I want that to break off the top 25% of my athletes, right? I want the biggest 25% of the guys, right? The ones that like can take the big hits and lose teeth. So I want this to be 25%. I want to know where that cutoff is. So when they stand on the scale, I can just look at the scale, look at the number, and say, oh, you're bigger than, I'm thinking it's 192, making stuff up. It's greater than 192, right? Now, I don't know this for sure, but I'm trying to ask the probability gods for it. So then you'd use inverse normal, because here we're giving it probability and it's giving us this boundary, and it's like spitting back the boundary. So you'd say inverse normal. The problem is inverse normal works from filling up from the bottom up to your limit. So if this is 25% and I put 25% in inverse normal, it gives me this lower limit. It gives me where the bottom 25%, like the skinny little dorks like me, where that cutoff is, right? And I don't want that. I want the upper 25% of the guys. So I need to put in 75%, right? I need to put in 1 minus 0.25, excuse me, which is 0.75. So we're going to play that game with inverse normal. So go to distor, inverse normal. The area is 0.75. The mu, again, is 190, and 7, right? And we say go, baby, go. And it spits out 183. Ah, it was low. So this is 183.72. And so we're rounding to 3 sig figs, so 184, right? And so those are the 184 centimeters. Oh, it's not weight, sorry, it's height. 184 is like the cutoff if you're for being in the top 25%, right? So the guy who's 183 is in the bottom 75. The guy who's 185 is now in this top 25%. Sweet. Ka-ching. Try some of those problems in your packet, and I'll see you next time.